Let's take a look at this near-infrared diode laser. It was built by a departed grad student, and what we know about it is it has a wavelength of 850 nanometers. It's continuous wave. It's at 0.8 of a watt, or 800 milliwatts. Again, we're going to be using the ANSI default exposure duration, which is 10 seconds for the near IR for an unintentional or accidental exposure. Now we've selected 1 over e squared because if we're not given that information, 1 over e squared is will give us our most conservative result and realistic. Circular Gaussian, we know that we have a beam diameter of 2 millimeters, but we don't know what the divergence is. So that tells us we're going to set the m squared beam propagation factor, or beam quality factor, to 1. That's the theoretical limit for m squared. And what that means is for a given beam diameter, if we set m squared to 1, it will calculate the minimum divergence that that particular laser or that laser output can have. And so this gives us, of course, our largest NOHD, and that's what we want to be able to calculate, is what is our realistic worst case NOHD, and there it is. Okay, now we've set our observer range to 0.5 meter. We can see that the diameter at range is just a touch over what we had at the beam waist. We have an OD at observer range of just a touch over 3. Worst case is touch over 3. And we can verify that that's the reason these are the same is because the power through the limiting aperture where the observer is standing is 100%, and of course the worst case is based on 100% of the power passing through the limiting aperture. Okay, and then here is the radiance calculated using the power through the limiting aperture and the area of the limiting aperture. This is the irradiance of the laser, and it's compared to the MPE, and the MPE in this case is about 2 milliwatts per square centimeter. Now the MPE for the skin is about 0.4 watts per square centimeter. We have a times skin MPE of 20.8, so this laser is going to be a bit of a hazard to us. And you'll notice that it's in the sort of the same range as when we're looking at a visible laser, but you can see that the skin MPE is much more restrictive for this near IR wavelength than it is for the visible, and that's what causes, even though we're running a much lower power, say, than if we were looking at that frequency doubled vanadate at 10 watts, which was about 33 times the skin MPE. This MPE for the skin being 0.4, remember for visible, this were for a quarter second exposure in the visible, that works out to be 3.11 watts per square centimeter. So this is a much more restrictive MPE for a 10-second exposure than visible for a quarter second exposure, and that's why the times skin MPE is sort of in the same ballpark as that much higher power visible laser. Okay, so 20.8, is that a skin hazard? I would say yes. That's, you'll certainly feel that. All right, and so we want to make sure that the user is aware that this is a skin hazard, and would, in this case, because it's a near IR, we certainly want to make sure the user is aware of this, because since you can't see the beam, it's more likely that you might stick your hand or arm in it, and you just want the user to be aware that this is definitely a skin hazard. Let's look at the NOHD. It's about 586 meters. The NSHD is only 41. Of course, that's because of the difference of the MPEs here. All right. Let's go over and take a look at the diffuse reflection hazard. You can see that we have a 2 millimeter beam on target. Observer range is a quarter of a meter. The exposure duration is 600 seconds, and this source type is extended. We have an MPE of about almost 7.5 milliwatts per square centimeter, and we have no NHC though for this diffuse reflection based off of this power limit. So there's no NHC, there's no OD required for the observer. We can look at the skin NHC and then time skin MPE, and we can tell that for a diffuse reflection, this is not a skin hazard. Let's go ahead and take a look at the correction factors. Let's look at the angle here, the angle subtended. That gets us the why this is an extended source, and we can see that the angle subtended is 5.66. If you start backing the observer out, of course the angle is determined between the observer and the beam on target. So if I back the observer out, we would expect to see this angle subtended decrease. So let's back the observer out. Let's go out to 1 meter. Oh, what we did is we crossed over, and it's to the point that it's not an extended source any longer. It's a point source. I wonder where that might be. Let me just take a couple of moments here. Oh, okay. Let's go 0.8, and we'll just kind of go back and forth until we get this. 0.85. We're getting close. 0.9. That's pretty close. You can see how this works, and then eventually, of course, we go out far enough. I guess I'll continue on, and that's too far. So we've got this just about narrowed down, and there it is. 0.94 meters is the crossover for where it's an extended source and it moves to a point source. So it really depends on where the observer is standing as to whether you have an extended source or a point source. And again, let me point out that the reason we have a source type is this is a near IR wavelength. And so we are within the retinal hazard region, 400 to 1400 nanometers. So we can have, because we reach the retina, we can have a point source or an extended source. Outside the retinal hazard region, there's no such thing as point source or extended source. All right. So let me put this back to 1/4 of a meter. Okay, you'll notice that C sub A is changed here. Remember, C sub A for a visible wavelength was 1, but here it's 2. And what this is, it is a correction factor for correcting the MPE for the absorption curve of the retina through the wavelength range. So that's really what C sub A is doing. It's correcting this. If we take a look at C sub E, which again, we don't really have C sub E of small t. That would be for a pulse duration. So it will be the same as for Tmax is 3.77, and that's the number that is being used to help correct the point source MPE to an extended source MPE. All right, I think that about covers it. Oh, one last thing, looking at a barrier. Let's say I'm 2 meters out with this barrier. I would need a barrier that would could withstand, I've got it in 1/E, that would withstand at least 40 watts per square centimeter. All right, that's about it.